this is the last session of the day, and it's been a full 2 days, so I want to thank you all for joining me here this afternoon. We'll get right into it. So how did you first get started with Ansible? First started using Ansible at JCrew, of all places. We basically had a consultant that had come into the e-commerce organization and was looking to use that to fully automate the e-commerce stack. He was actually fired before that happened, so I sort of picked up in his place and started using Ansible to deploy essentially a WebSphere application. So that said, it's been a few years since JCrew, so I've been using Ansible for about 4 years. And my favorite thing to Ansible right now is basically deploying templated Kubernetes manifests for common services in EKS, which is Amazon's Kubernetes service. Okay, now we got that over with. This is the Scaling Ansible for IoT session. If this wasn't what you're looking for, please stick around. I promise you'll learn something. So just an agenda. Basically, we'll talk a little bit about myself and Intersection, some of the challenges that we faced with our IoT products and IoT in general, the general architecture of the solution that we built to maintain all of these devices, and then sort of what a sample deployment looks like in that pipeline. And then at the end, I'll take questions. So again, if you missed it the first time, my name is Brian Annis. I am the lead site reliability engineer at Intersection. Intersection is essentially the combination of a media company and a technology company. And we essentially tried to build like digital experiences in physical space. Exactly what that means generally boils down to real-time advertising and wayfinding. And we'll get I'll share a little bit more about that in a moment. Basically, today, our engineering team oversees over 7,000 IoT devices strewn across the globe. And we have two general categories of products. So for any of you that live in New York or have been to New York anytime probably the last 3 or 4 years, you may have seen our Link kiosks. So this specifically is Link NYC. These are smart cities kiosks. They have a bunch of features, but primarily there's two 55-inch displays for showing ads or PSAs, public content, so on and so forth. There's also free gigabit Wi-Fi, so if you need to catch up on Game of Thrones, you can do it pretty much anywhere in New York City without blowing through your data cap. And then there's also a tablet that offers emergency calling, rapid USB charging, and other city services on that little screen at the bottom of the pedestal. So, either side of the house, we have our transit product. And so if you live in any of the cities that we've deployed these kiosks, this may look familiar to you. Essentially, we have two types of kiosks. One that we call InTouch. I didn't make up the name. But essentially, these are interactive touchscreen kiosks. Generally, for the transit authorities, it's some sort of combination of transit alerts, if a particular train is not going to stop at that station, if there's no service at that station, wayfinding, so how to find your way from one station to another within the system, and then also advertising or other interactive content that may be scheduled on those displays. So we have a number of these all over the country, including the MTA. We also have a deployment across the river in New Jersey. Following that, we have another deployment a little further south in SEPTA, which is in Philadelphia. Most recently, I think probably 2 years ago, we started our deployment in the CTA. These InTouch screens are now deployed all over the Chicago Transit Authority. And then our latest deployment is actually in LA Metro. So for any of you that live in LA, if you go on the Blue Line in Compton, these were just installed a few months ago. And then the other part of that product suite is Insight, which is basically the same sort of experience minus anything that might be interactive, right? So there's no touchscreen for these guys. And similarly, we have these deployed in TAs all over the place, including, again, CTA and also the Minneapolis metro system. So just as a quick survey, has anyone in this room actually seen one of these in real life? Okay, we got one. We got one guy. Okay, great.
Why village people?
No worries. Okay, so just to give you an idea of the sort of where these things are strewn out across the world, this is our nationwide digital deployment. So you can see we're in a number of top 10 DMA markets. And then we also have a fairly sizable deployment in the UK with InLink UK. So if you've been to London or any of the surrounding cities, you've probably seen the Link kiosks there as well. Okay, so what are the challenges with IoT, specifically configuration management for IoT? And as we sort of work through what the table stakes are, let's just keep a couple things in mind. One is our initial assumptions. So sort of as table stakes, right, we sort of assume that any IoT device is a low-powered system on a chip, right? It's some sort of embedded device, think Raspberry Pi or similar like cut-down Intel board. In the same breath, like for our specific conversation today, we'll be talking about devices that require a live display. So if you think like a Nest thermostat, a digital advertising kiosk, or like an Echo Show, right, Google Home Hub, all of these have a live display, and then we'll get into why having a screen complicates configuration management down the line. Okay, so one of the challenges with IoT is essentially your device needs to support heterogeneous networks. And what I mean by that is that it has to basically support everything under the sun. So for one, like when we deploy many of our screens, we are using a combination of connectivity that's available to us. So in this particular example, we're showing that any of these kiosks could be connected to a partner TA network. That's actual hardline connection that the transit authority provides to us as either fiber or Ethernet, or they might be using LTE from any number of national carriers. And that strictly boils down to, is there existing cabling? Do we have to lay conduit? Is the TA okay with laying additional conduit, and what the costs are? In the same breath, a lot of these TAs don't allow direct inbound access. And so, if you go to, let's say like the CTA, just for instance, and you're like, hey, we'd like to open up 22 on your network to these screens, they're gonna laugh you out of the room, right? And as you can imagine, that sort of like puts a pretty firm halt on deploying Ansible in sort of the normal topology. Another thing we have to deal with is hardware variety, right? So where we're dealing with street furniture, street kiosks, generally it's assumed that the structure will last around 10 years or so. But the important thing to remember is that even these embedded SKUs that we buy for the boards, like the single board computers, while they may be available for 5 years, they're not going to be available for the whole life of the structure. And so we basically need to plan from the beginning to support multiple types of boards, even within the same sort of class of product or class of structure. The other thing that can make this complicated is that we have to support new hardware that TAs may give to us as part of ongoing new contracts, right? So if we were to go into a new transit authority tomorrow and they already have an existing smart screen or smart kiosk provider, generally they will own it as part of that contract, and then we will take over management of it. And so this really opens up the floodgates because we have no idea what is deployed there, how old it is, what architecture it is, so on and so forth. So this also complicates things. Just generally within the realm of embedded computing, there's also a number of challenges. So I'm sure many of you have played with Raspberry Pis, either at home or at work. One thing that can be tricky with single board computers or just embedded computing period is that sometimes they don't include a real-time clock. So that is a hardware clock that has some sort of battery backup so that when it's not connected to the internet, it still is able to keep accurate time. And this makes maintaining things like SSL connections really tricky, right? Another thing we have to keep in mind is that these embedded boards may have alternate CPU architectures, so may not be dealing with Intel, may not be even ARM, it could be RISC, or it could be MIPS, or it could be even PowerPC, right? And so we need a solution that basically can work on any sort of CPU architecture. Okay, so here's another one. We can't talk about IoT without talking about security. So when you're operating in a public cloud or you're operating in your data center of choice, you have a number of things that either the vendor does for you or you can do for yourself to really secure that environment, right? Physical security, ACLs, the network, so on and so forth. When you operate in public space, a lot of that just doesn't exist, right? We may be able to lock the device in a cabinet, but it's not going to prevent somebody from hitting it with a dump truck, right, and gutting it. So basically, security has to be a first-class citizen, and we need to ensure that we encrypt everything everywhere to protect both our IP and our transit customers. Okay. And in the same breath, like traffic management. So anytime that you have several thousand computers that are all reaching out for, it could be a software update or a package or whatever. And this even includes like, corporate, office fleets, right? You could DDoS yourself, right? And so there needs to be some way to manage the traffic for these configuration management runs to prevent you from essentially DDoSing yourself. Another thing to keep in mind is that a system designed to manage these devices can be eventually consistent, right? Like we don't need to have, sub-millisecond consistency across all these devices at once. In fact, that might actually be dangerous depending on the contents of the release. And so we have some flexibility there with our solution. Okay. And I know I talked a little bit about screens before and how for this conversation, the screens are sort of critical to the CM solution. So as opposed to like an Alexa or a Canary device, and if you haven't heard of either of these, please feel free to Google them, but they're basically small consumer electronics. You could very easily deploy containers to the edge and use containers to essentially manage your configurations for those devices. But because we operate physical screens in physical space, there's a number of additional considerations there, right? One is that because we're out in the physical world, there can be physical events that prevent these devices from working. Could be hit by a truck, could be water ingress, could be a fiber cut, in a manhole cover somewhere in New York City. And all these things will actually bring that device down, right? In the same breath, we also need to adapt our monitoring to understand the components of a physical display, right? The backlight, the display controller, the actual X session that's running in Linux, and how all of these things work together to determine display health. Okay, so beyond all of those challenges, I know that was a lot of challenges, Intersection also had specific challenges to their implementation prior to our re-architecting. One of them, as I mentioned previously, was time synchronization. So we had unreliable time synchronization on certain devices without real-time clocks. We'll talk more about that later. Visibility. So we had very limited metrics on deployments, the status of deployments, and any issues that might be happening in the fleet with the legacy solution. And hand in hand with that, we did not really have a broad end-to-end release testing system for those CM releases when they went out. And as I sort of alluded to earlier, like one thing that can be really hairy when trying to build a CM solution without being able to rely on TLS is that you can't rely on TLS, and the content of your release needs to be encrypted. And so we had to find a solution that allowed us to maintain encryption of our payloads without jeopardizing or just relying on unencrypted connections. From a visibility standpoint, I sort of alluded to this earlier, but we didn't really have a global metrics platform, so it was very hard to gauge the success of the release. And because a lot of our alerting was log-based, it was trailing, and so we would find out that there were problems way after a release had gone out, which is obviously problematic. Okay, so I know that that is a lot of challenges, but basically to recap, we have thousands of low-powered computers. They are dozens of discrete networks. They're operating globally in public space, and they're equipped with physical displays. And it's occasionally January 1st, 1970. Okay, so how did we solve this problem? Basically, from an architectural standpoint, we knew that we had a couple key goals, right, as far as our solution went. One is that the solution should be fully managed in a GitOps compliant way. And I'll get into what I mean by GitOps a little bit later, because it's like DevOps, like a buzzword. Two, we need to basically ensure transit encryption, right? So that those payloads between our source of truth and our devices are encrypted without TLS. Three, it needs to be able to scale to thousands of nodes across multiple geographic partitions and multiple different types of networks. And four, finally, the release needs to go through a whole suite and battery of tests that are automated that can give us basically advanced validation of a release before it rolls out to the world. Okay, so it's time for something a little bit different. basically, and I would guess that pretty much everybody in this room has used Ansible, or at least has read about Ansible in push mode. So we're going to talk about using Ansible in pull mode. What is Ansible pull? So basically, Ansible pull is a wrapper around Ansible's Git module and around Ansible playbook. And what it does is it allows you to essentially define a Git repository to pull down and then execute playbooks contained within that repository locally. So because we are operating in pull mode, this basically allows us near limitless scaling for our configuration management solution. Some features of Ansible pull, you can use multiple different types of checkout targets. So you can use a combination of branch name, tag name, or commit ID. They also include a number of helpful arguments to deal with your release management. One of them is jitter, which is basically adding some randomized delay to the execution of the run. Clone depth, you can say basically just pull down the last commit, so I don't have to pull down the entire repository. And directory cleanup. Hey, if something goes wrong or in the middle of a clone, if something isn't right, just give me the contents of the repository. And here's an example of what that looks like. So you can see that we're very similar to Ansible playbook. We are defining an inventory. We have a branch name. We have a GitHub repo. And then we're also defining a sleep arg, basically to delay that upon instantiation. Okay, so from a very high level, this is what it looks like. Essentially, we have our engineering organization, our SRE team here on the left. Our releases are pushed through to GitHub via a CI system. And then all of the devices themselves connect to GitHub directly and then send metrics back about the status of the release to our metrics platform. So let's break that down a little bit. What does the engineering component look like? So from an inventory perspective, we also do things a little bit differently. While you may be familiar with traditional INI style or dynamic inventory, we are using the alternate directory-based inventory structure, which is essentially a folder per inventory. We're also using an external metadata service to steer our actual Ansible run. And I'll talk a little bit more about that in the next slide. But essentially, we use a metadata service that writes local facts to disks, and then those facts are consumed by the run. Why is this important? So in terms of the metadata service, basically, we wanted to be able to decouple certain facts and information about the device and what it should be doing from the actual Ansible run itself. And the reason that we do this is basically to enable a fail-safe execution, so that if you were to look up this data dynamically within the run, would say like a dynamic inventory plugin, if no inventory information was available, the run would fail. And so by persisting this to a local cache and decoupling it from the run, we prevent that from happening. In a complex organization such as Intersection, obviously we have many external metadata sources. Using this external metadata service, we're able to essentially combine those multiple sources of truth into one fact list, if you will, that Ansible can understand. So from a transport encryption standpoint, as I mentioned before, we can't rely on TLS, and this is one of the things that really shaped our implementation. So basically, we are using RSA keys to access GitHub and clone down that repository so that we are able to securely move the payload from GitHub to the device without TLS. As you may imagine, because we are using RSA keys to create the connection to GitHub and then move those files, we also need to make sure that the keys only have read access to the repository, so that a compromised device would not be able to commit changes back to the repository in a supply chain attack. As far as run scheduling, we try to keep it fairly simple, but predictable over certain periods of time. So basically, we are leveraging native systemd services and timers. So if you have used systemd in any sort of manner, this should all sound pretty familiar. As far as traffic management, as I mentioned previously, we need to avoid DDoSing our services. So we employ jitter within the timer itself, and then we also use systemd timer randomization to basically not hit all these services at once. And here's an example of what that systemd file looks like. Obviously, this has been redacted and simplified for the purpose of this presentation, but essentially, I'll point out some key elements here. One is this bit right here. So you can see that there are 3 services. We have one that is triggered on failure. So if Ansible pull ever exits with a non-zero, essentially, we want to run this AP reset service to restore health. We also have this AP updater service. And notice that it is both using once and before. And this is to enable mutual exclusivity between this service and the updater service, which we'll touch on in a moment. But beyond that, you can see that this all looks fairly familiar to just running Ansible pull locally. So as I mentioned, we have that reset or recovery service in there as a on-error target. And the reason this is important is because, again, we have a lot of these devices in physical space out in the world. Their network connectivity may be intermittent at times. And so we basically need to ensure that we are doing all that we can to remediate the health of that device without rolling a truck, because that's really expensive. So essentially what the recovery service does is it runs a script to try to restore device health to the best of its ability. Obviously, we can't prepare for every eventuality on a device, even with very strong CM. But we can try to bring it back into at least a serviceable state. The reason this is important is that we essentially want to ensure the run capability at all times. So that, for instance, like if there was a git clone error, that the directory is being removed and git can try and clone again on the next run. And so an extremely simplified version of this is shown here. Essentially, we have a bash script that is removing that pull directory where the repository is stored. And then we also have an example of like a virtual environment being checked for corruption and then being removed if it is corrupt. So certainly, completing the triumvirate here is our upgrade capability. So we need to be able to provide a self-upgrade capability without using Ansible to upgrade Ansible. And so the way that we do this is that we actually are using Python and native Jinja templates that you could use in Ansible to create the systemd unit that actually runs the agent and populates that with the facts from the metadata service. And so what this allows us to do is essentially change the, you can change like what a device is by simply changing the parameters in the metadata service without having to resort to other means. And so why Ansible pull? So with everything we just discussed, basically boils down to 2 things. One is that we are able to securely manage devices distributed all over the world by having them talk to GitHub and not relying on essentially a tower installation for every TA, or relying on inbound 22 access to every device in our network. Hand in hand with that, we are also able to scale basically up into the limit of the number of connections that GitHub will support at once, which is a lot. So certainly, we haven't gotten any angry calls from them, so this isn't so much of a concern right now, but when they host companies such as Autodesk that have 10,000 developers that are constantly committing, our read-only traffic should be fairly predictable compared to the sort of challenges that GitHub faces. And so now we'll move on to what the actual GitHub implementation of this looks like. So if any of you have used Git before, you may have used Git flow. For this architecture, we use GitHub flow, which is essentially a simplified version of that. It more or less leans on creating a feature branch. You can commit to it, make your changes, and then when you're ready, it goes through a PR, basically reviewing that branch for changes, and then it gets merged to master. on merge to master, your change set is deployed. And so what it looks like for us is because we use feature branches for creating those atomic change sets, we actually are able to create essentially a local development environment just by creating a branch. So if you've worked with other configuration management systems, you can know that it can be a bear or basically impossible to set up a desk version of it. With this architecture, it's trivial to do so. Any branch can essentially become a development environment. You can do whatever you want in it. It doesn't affect any of the other environments. And you can point your local desk device to whatever branch that you are working on, and it will be made manifest within a couple of minutes. And so this brings us to what is our fairly unorthodox branching strategy, but it is because of the way the Ansible pull works, right? If you recall, you can either target a commit, a tag, or a branch. So for constantly pushing changes to many of these devices, we can't use a commit or a tag, right? But what we can use is a branch. And so essentially how it works is that once your feature branch has been merged to master, our CI system takes over. And I'll get into how the CI system works a little bit later on. But essentially, each one of these branches represents an environment. And we mean environment in a truly global sense. So we may have like many different customers, many different zones, so on and so forth. But everything that is a production device serving customer traffic is connected to the production branch, and so on and so forth. And so what does our Git workflow look like? Pull requests are required, right? So if we're using branches to sort of act as mini pipelines, if you will, or a larger pipeline, you have to do PRs to get your changes merged into master. And that's essentially where the merge train starts. So in our organization, that is shepherded by the SRE team. And then the other important part is that CI manages the releases. So there's no humans involved once your change set is approved and merged to master. And that's also by design. We don't allow write access for humans because it could be really easy to merge your feature branch directly into the production branch, and then bad things would happen, right? So why Ansible pull in this specific topology? So one is that basically we can use GitOps. Everything goes through GitHub. We can use GitHub Flow to manage our infrastructure just like we manage everything else. Another is environment visibility. So if you wanted to know exactly what is in QA, global QA, you want to know what's exactly on every canary device in the world, you just need to change your branch to that branch, the same name, similarly named branch, and then you can see exactly what is on those devices. So the third part of the triumvirate here is a combination of AWS and our CI system. So at intersection, we use BuildKite. If you've used Jenkins or literally any other CI system, the primitives are the same. Essentially, every commit starts a CI run that runs unit and integration tests for Ansible. Upon merging to master, CI also, as I mentioned before, manages the release and the merging of that code to those downstream branches. So what kind of tests do we run? Obviously, the developers and maintainers of Ansible run their own unit and integration tests on the actual Ansible code, so we are not focused on testing Ansible, right? But we are focused on testing the intent and the outcome of Ansible, right? And so we do two things here. One is linting and validation, essentially making sure that we have valid YAML and that we're not committing any gotchas, any bad Ansible practices on each commit. And then we're also running unit tests for code, Python code specifically, that may be packaged alongside our CM solution that doesn't live in like a separate Debian package, more or less. And this is an example of what that looks like. So you can see that we are checking for our valid YAML. We're running a bunch of tests. Basically everything that you would expect. If you see some of these black bars here, obviously some things have been redacted for this talk, so don't be too worried about it. So from a testing standpoint, we move on to sort of a more stringent level of testing. So we run integration tests in Amazon. We essentially have EC2 instances that mimic these physical devices, and we do an end-to-end Ansible run and see if it's successful or not. We terminate those instances after each run to basically ensure that the previous run did not have any effect on the outcome of your specific commit. Finally, before you merge to master, you are also required to run a lab test where the CI system actually executes an Ansible playbook run on physical hardware that matches what's in the field. And here's just an example of what that looks like. So this is the actual pipeline that we use for this product, and you can see each of the steps that I've talked about previously. And then we can also see those merge steps that I alluded to in the Git section. And all these are doing is just merging from the downstream branch to the upstream branch. And so no CM solution would be complete without metrics and visibility. At Intersection, we use Datadog for this. If you have not used Datadog, it is an absolutely fantastic tool. I would highly recommend it. We send two types of data to Datadog. One is release events. So essentially our CI pipeline that I previously showed sends essentially an API call to Datadog to tell it that a release is going out. And this allows us to bring release events into other dashboards that Datadog provides. Another is release monitoring. So we capture a ton of metrics from the releases, but the important ones are essentially the commit age of everything in the fleet, the number of devices on a specific commit, and the health of all those devices in real time. And so this is an example of what a dashboard that does that might look like. You can see here that there is a heat map that essentially defines what every commit that is being run in the fleet looks like. You can see that most of them are on one. You can see that there are trailing ones. And because there are trailing ones and we can visualize them, we can actually look and see why those are stuck on old commits. And this helps, again, raise the visibility of what could be going wrong in the fleet. This is not a particularly great visual, but what these three graphs show is essentially the disparity of commits over time. So if you were doing a release, you would see the various branches converge, or rather they would converge over time. And so they would start split and then they would converge over time as that commit makes it through each branch, right? Each chunk of the environment. And so some things we get out of Datadog, one of them is visibility. So we have native reporting. We use the Ansible Datadog module to send the status of the run to Datadog directly. And then as I just showed, we are also able to use Datadog to surface outliers. Hey, why are all of the links in this neighborhood not working? Or hey, why is all of link not working? These are the things that we can see very quickly in our metrics platform. And hand in hand with visibility is obviously the alerting portion. We want to know when stuff is not working as intended. And so we can use these metrics to monitor the fleet-wide status for any customer, any particular zone, any geographic region, any version of the code base, so on and so forth. And we're also able to use Datadog checks, which are essentially a form of monitoring that Datadog provides, to provide individual component health. And so we can tell if there is a problem with a link only on one side, on both sides, all of the components in an entire neighborhood, and so on and so forth. And so just to recap, you can see that this architecture basically allowed us to meet all of our goals. It is GitOps compliant. I'd say it just is GitOps, right? We basically use RSA keys to ensure that transport level encryption. This can scale to thousands of devices across the world, basically up until the limit of when GitHub throttles us. And lastly, each release is tested and validated by a CI pipeline, and all of those tests are automated. And so what would an actual deployment in this architecture look like? First, I just want to share this quote from Scott Weiss. He said, with IoT, we're headed to a world where things aren't liable to break catastrophically, or at least we'll have a hell of a heads up. And I really enjoy this quote because I feel like with IoT, it is a combination of two things. It's like, because everything is connected, things could go badly quickly everywhere. But in the same breath, like if you have a proper release pipeline and you have testing and you have confidence in the release, then yes, you should have a heads up before things actually go south. And so just to walk through what the sort of developer experience looks like, you would create your feature branch and you would commit your atomic changes to it. You would test that in our integration environment in BuildKite. And realistically, you would also test this at your desk, right? You're setting your desk single board computer to connect to your branch, and you're running, Ansible pull locally to see what that looks like. Basically, once you merge to master, you are in the pipeline, right? And so you are blocking the rest of the pipeline until your release is either all the way through to production or it is superseded, fixed forward by another release. So basically, as your change set is validated in each environment, in QA, and then Canary, and then finally production, you can go to the next stage. And finally, once you have completed the release, or more accurately, during the release, release metrics are sent to Datadog, and then you're able to see that in dashboards and the actual checks, as mentioned, to determine device and fleet health at large. So just to show some vanity stats here, we have achieved quite a bit of velocity with the structure and scope of our fleet. We do over 50 releases, 50 infrastructure releases a month. We have almost 4,000 commits on this repository. It's about 2 years old, and then we've had over 22 contributors, including a number of folks that are new to Ansible for the first time. I would be remiss if I didn't plug Intersection. We're hiring, so if any of this stuff sounds fun or interesting, the SRE team, my team, is looking for some folks to come on board and work on cool projects like this. We also have a massive AWS fleet that is also managed by Ansible, so if you like Ansible, please come talk to me. And with that, I'll take questions. Yes?
Okay, so it's all...
Do we have the mics, or? Just want to make sure the audio is recorded.
Oh, okay. Yeah, if it's all handled through single board computers, because it's all controlled by some form of Red Hat?
Yeah, so great question. So the question was, because they're single board computers, are they controlled by some version of Red Hat Linux? So it is Linux, but it is not a RHEL derivative. So we were talking about IoT throughout this entire presentation. Like the devices do run a Linux operating system, but it is not, as I mentioned, a RHEL distribution.
That way, so Ansible can be on the installation of the OS?
Yeah, it's for all intents and purposes, it's just Linux. So it doesn't.
What happens if that local installation on these IoT devices goes up, bombs out, or fails of some sort?
I'm sorry.
Or the local installation of the OS on these devices go out. How are you able to?
Yeah, so so the follow-on question was basically like, if something happens to the device, right, at the operating system level, how can you recover it? So, as I mentioned, like we face a fairly unique deployment challenge, which is to operate tons of computers everywhere with no, like physical bounds, basically. So if it was in a data center, traditional data center, you have out-of-band management, and you have all of these types of tools to ensure that you can, bring the machine back to with a fresh OS and so on and so forth. We don't have that capability, right? So we essentially try to maintain device health to the degree that we can with the reset capability or with the actual Ansible agent itself. With certain products, we have the ability to restore them to essentially an image. But for the most part, that capability does not exist. Any other questions? Gentleman in the back. I'm sorry, what did you say?
How often do you configure the pull process?
Okay, great question. So basically, how often do we run Ansible pull? So we run it essentially every 20 minutes plus a 5-minute jitter. And so we can say that, within a 20-minute span, it may not have run, but it certainly has run twice within an hour, and then, certainly many times throughout the day. Looking at that 20-minute number was essentially trying to balance seeing the results of the release go out with not waiting forever because we're taking things slow. So certainly with the as the fleet grows, we may change that. We have the capability to change that using the updater service, but it's totally dependent on the size of the fleet.
Follow-up question. Bandwidth, how do you throttle that?
Okay, so the question was, how do we throttle bandwidth, or how do we deal with bandwidth? So for the most part, because we are on a variety of networks, there are certain constraints that, let's say, to a particular customer. So maybe Transit Authority 1 will only give us a set amount of bandwidth on a set VLAN, and other TAs may just give us dark fiber, and we can just do whatever we want, right? So generally, we essentially use the jitter and the timers to essentially tranche in real time the amount of devices that are connecting to any upstream service. Everything the devices connect to is largely scalable, so many services in Amazon that can take tons and tons of traffic. But in terms of the actual on-net conditions for the TA, we essentially have relied on that auto tranching behavior with the jitter to manage that for us. Any other questions? Gentleman in the center.
Yeah, why don't you deploy your own Git server? So right now you're relying on GitHub to manage your workflow. Why don't you build your own GitLab or Git repository? You could coordinate security, bandwidth, resources if you did that. So
yeah, totally. So essentially, we're a technology and a media company, right? So we don't necessarily need to be the best at hosting Git. GitHub has, in our view, more or less solved that problem, and so we don't really see it as a differentiating factor for our company to invest heavily in scaling Git. GitLab and a number of other providers, GitHub and another other providers such as GitLab have also figured that problem out, and so we're happy to use their services. Any other questions? Gentleman in the back.
Are you simply throwing up a splash screen during the deployment of these devices that are public-facing?
So the gentleman's question was, do we throw up a splash screen while these deployments are going on? And that's a great question. So this is another circumstance where, because we operate in public space, we need to be mindful of what's on the screen. So in terms of device boot, we do have a splash screen that hides essentially the Linux boot up. But in terms of the actual deployment, because the only thing that is on the screen is the add software, that is really only impacted if the software itself is updated. And so generally that is scheduled outside of normal hours, where it's it will go down, but it's for a minute, right? So
great
yes.
presentation. My question is, how do we manage security patch management, security patching on a global scale? So if you have to push some patches to all your IoT devices, what would be your strategy?
Yeah, great question. So how do we manage security? Essentially, because one thing that is a huge boon to us is that we are using Linux, and so that is a lot easier than using other platforms. But essentially, if this architecture sort of sat in your mind and is beginning to sort of settle in, this is an important thing, right? And so essentially what we have done is that there is a way to tranche releases further. And so let's say that there was a new kernel, right, and you want to install the latest kernel. If you install it on all 7,000 devices, even with the tranching, you would probably blow up some bandwidth, as the gentleman in the back mentioned previously. Or if there's a bug and then all of them just crash and boot loop forever, then you don't have a business anymore. And so essentially what you can do is, because we are leveraging that inventory as a directory structure, what you could do is essentially include what we call canary logic is a bad description of it, but essentially group logic within the run, where if a specific, so even though an inventory, let's say the production CTA inventory has this version of Linux, if you include an override in that inventory's group vars, then just the CTA will get it, even though the production contents of that branch are live everywhere. Does that make sense? So it can be kind of strange to like wrap your head around like the branching structure. But if you combine that with the native flexibility that Ansible gives you, then you can deploy anything you could deploy normally with Ansible in that method. Does that make sense? Okay, perfect. Any other questions? Okay, great. Thank you so much, guys. Really appreciate you coming out and hearing us talk.